Ramakrishna has already covered quite a bit of details in classical control. So he has covered Laplace transform, the transfer function modeling, stability analysis in root locus, Bode, so on and so forth. What I would like to do in these series of lectures is to go to the other design of control, other option of control systems, which we call as modern control systems. And specifically in this lecture, I will be talking about state space. All right. So we will see what is state space control or rather state space systems. We will see some modeling aspects of state space systems. I will present a few examples in this, and then we will go ahead with other aspects as well. Okay. So first of all, we have already seen what Professor Ramakrishna has already taught about the transfer function modeling approach, and the question naturally arises, why do we want the state space approach? All right. So before we go to the state space, let's see why we need a different approach as compared to the Laplace transforms. So on the slide I have got two boxes over here. On the left I have got the good aspects of the transfer function approach, on the right I have got the drawbacks. So transfer functions is actually very useful, and it is actually one of the most dominant forms of modeling in the control industry. So you go for process control, aircraft, any kind of systems, ships, so on and so forth. The dominant way of modeling a system and then controlling it is always from the viewpoint of a transfer function. All right. So the basic concept of a transfer function is that it is some kind of a generalization of the Fourier transform. All right. So once we see that we are in the Fourier transforms, we know that we are essentially trying to have a signal processing viewpoint of a system. So you have a system and you give inputs of varying say frequency, and the output is measured with respect to these inputs of varying frequency, right. So this is more a signal processing viewpoint, and more specifically this is called the input output view. And because we are looking at signals with frequencies, a natural aspect that arises is the notion of bandwidth, all right. And we know that bandwidth is very important for control systems. If your bandwidth of the system is fairly low, you cannot control the high speed dynamics, all right, or you cannot analyze the high speed dynamics, and vice versa. If the bandwidth is too high, you may start to bring in lots of noise and other aspects, all right. So the bandwidth is of course dependent on the specific task and the problem which you are looking at, but the bandwidth is again a very specific aspect of the signal processing viewpoint, and it's a fundamental aspect in control systems. The other nice aspect of control system of the transfer function approach is that we have these algebraic properties of transfer functions. So I can take multiple transfer functions, I can put them in different say I can cascade them in parallel series, I can take the feedback loops, feed forward loops, so on and so forth. So the idea is that I can actually combine different transfer functions by using their algebraic properties, right. So we have seen that you can just take two transfer functions in series and you can just combine them by the product of them, or I can take a transfer function, I can do a feedback with another transfer function, you know, so on and so forth. And all these properties I am able to combine these different blocks primarily because of their algebraic nature, all right. So it allows us to do a lot of very useful things by combining different blocks from different subsystems, and we can build more and more complex systems, right. And of course, as I said before, this is very dominant in the industry. You can take any advanced industry in the world today, transfer function modeling is the single most important aspect when we come to the control of any system, all right. So that is a good stuff. Let us see what are some of the drawbacks of the transfer function approach. The first and most important is they can be used only for linear systems, all right. So we will go a little bit about what we mean by linearity and so on in the next lecture, but for now I am assuming all of us have a fair idea of what is linearity. So transfer function approaches cannot be easily used when we are looking at nonlinear systems. It can be done, but it is a little bit tricky. Okay. Secondly, the other important thing is it is usually limited to single input single output systems, right. So, I have got a system like this, say a transfer function over here, I have got an input and I have got an output, right. So, it is basically limited to these kind of systems. Now, in general we see that a lot of systems are of the multi input multi output type. So, I have got different inputs, and for each input with the combination of a particular process in the plant, I have got different outputs, right. So, y1, y2, so on till yn all the way to gn of s, right. So, I have got inputs r1, r2, so on till rn of s. Now, we know from the lectures that Ramakrishna has already explained, we know how to handle this system, right. We also know how to handle this system. We know how to handle every individual system in this particular say highly complex system, which is an interconnection of many different systems. What we still have not seen is when two systems are interconnected, all right. So, I will actually give a specific example and then it is going to become clear. So, let us take I have got system 1 over here, system 2 over here, right. We know how to analyze the stability properties, we know how to compute performance criteria, all these kind of things for each of these individual systems. You take any complex system, a chemical process plant, aircraft, automated autonomous vehicles, so on and so forth, you never have single systems, there are multiple subsystems and these subsystems are actually coupled to each other. All right. So, you may have the engine control system and then you have say for example, the automatic flight control system, okay, or in cars you may have the ABS system, the advanced braking systems which we have. Now, these are coupled systems. So, when we say couple, it means there is some kind of a relationship between these two systems, right, and these are very tricky to handle when you have multiple such subsystems, and the number of such subsystems in a advanced vehicle or a chemical process plant can go to hundreds if not thousands, right. So, for each one of these we need to keep on say modeling first in the simple single input single output approach, then we need to start to look at what are the coupling effects between these two systems, and the coupling can actually be nonlinear in many cases, right. So, this becomes extremely cumbersome when you have multiple input multiple output systems. Now, this does not mean that people are not doing this. So, in the aircraft industry for example, you have extremely high order systems and there is really very complex amount of say dynamics and controls which is required, and it is all done in the classical approach, right. So, you have beautiful transfer functions, you have these couplings between the say each of the transfer function loops which you are looking at, and you can model all of this. The problem with the reason why we had to do this in the good old days was primarily because computing power was very limited, all right, and we will see in a couple of slides why this change in the computing power allowed us to advance in the notion of state space and other modern control say techniques. So, the reason was because we had limited computing, everyone preferred to look at individual loops, design the controllers for individual loops, and then worry about the coupling between individual loops, all right, and then design another controller to take care of the coupling, those kind of things. So, this is obviously very tricky, and it can lead to really messy designs, and it is very difficult to really capture all the coupling effects, so on and so forth. So, that is another drawback. The final drawback, which is actually very important, is that the internal behavior of a system is not known. Remember that we just said that a transfer function is typically an input output view of a system, right. So, you give a signal over here, you measure the output of the signal, and that is all you are really concerned about. So, the transfer function then would be just give me a minute. So, the transfer function then would be something like the ratio of the output to whatever is the input which is applied, right. What is missing is the internal dynamics of the system, and it can be a very complex system, right, but we have absolutely no clue what is happening within the system. All we are concerned about in the transfer function approach is simply the response to a given input, that is about it, all right. So, these are the drawbacks, and let us see how the introduction of this new concept of a state space system solves many of these issues, all right. But first of all we need to see what is a state space system, okay. So, a state space system or a state space representation of a system is basically a mathematical model that connects the inputs, the outputs and the internal variables of the system called the states, right. It connects all of these three different parameters by first order differential equations, right. So, as we drew in the previous slide. So, as we drew in the previous slide, say for example, I have got this system, I have got multiple inputs, I have got multiple outputs, right. I will just write it as R1, R2, R3, I have got 2 inputs, but it does not matter, I can have 10 inputs, 100 outputs, yeah, so on and so forth, okay. And then there are multiple subsystems within this, right. Each of these subsystems is important because it shows how the input is mapped onto the output, and we will see a couple of examples of this later. So, a state space representation of this system, okay, what it does is to basically be able to take care of the inputs which I have, all the inputs, take care of all the outputs which we have, and all the internal variables which are actually hidden if you look at it purely from an input output point of view, all right. So, and of course the relationship between these three guys are essentially just first order differential equations, okay, and we will see why it is first order differential equations in a couple of slides, okay. So, classical example which I gave before, which I briefly mentioned before, was the chemical processes. So, I can give a very short example of that one over here, and there the idea was that let me, yeah. So, there the idea is that let us say you have this chemical process plant, okay, there is a chemical process plant, and you have multiple inputs, okay, I have just drawn 3 inputs over here, but you can have more, and you have a couple of outputs, right. Although in a real chemical process plant you would have at least 20 to 30 different inputs and hundreds of measurements which are the outputs basically. So, now what could be the inputs? So, one input could be the steam, the volume of the steam which is coming in from the boilers, right. The other input could be the pressure which the compressors in the chemical process plant are applying to the particular liquid which is inside this inside the chemical process. So, this is because of the compressors, right, and then maybe we are having additional inputs like maintaining the temperature and so on, right. So, these are 3 different inputs which are being given to your plant, and maybe we want to maintain the purity of a particular chemical that we are trying to manufacture. Say for example, we want 99.9% pure ethylene, right. For example, ethylene is something that is used to make plastics, the plastics that you see over here, and maybe you also want to measure the pressure and the temperature and the volume, because we do not want these plants to go into a catastrophic failure and blow up, right. So, these are the measurements over here, all these are the measurements, and these are the inputs to the system, and internally you have a lot of very complex dynamics going on, right, and the state space essentially manages to capture all these dynamics in one single framework, and we will see a couple of examples of this later. So, that is one very good thing. If you have to do this with the transfer function approach, as I mentioned before, you need to model each path separately, right, then you need to worry about how these things are coupled with each other, and this becomes very complicated. We will see in the state space approach why this is really very simple. The second nice aspect of state space systems is that we can actually isolate individual subsystems. So, the key word is this one. We can actually isolate individual subsystems and or say the components, and we can actually say that these specific subsystems, so to speak, are either controllable or uncontrollable. We can say that observable or unobservable. Of course, when we say components, we actually mean states. We do not mean literally the component itself, but the representation of the component, right. So, we are looking at a system where I can model inputs, internal variables, outputs. I can even tell which specific internal variables, the states are controllable, uncontrollable, observable, unobservable, so on and so forth, alright. So, we will see all this a little bit later. And of course, the other important point is that we will see that state space is the linear version of state space systems is entirely dominated by linear algebra, and there are excellent techniques and really good software tools for us to do analysis and design, alright. So, to recall, to summarize this slide, the basic idea is that a state space representation of a system is a mathematical model which captures your inputs, outputs through these internal variables called the states, and all of this relationship are basically first order differential equations. Okay. So, let us look at the general procedure to obtain a state space system. I will derive one or two examples a little bit later. The basic idea is that we have seen in the transfer function approach, whenever you are given a physical system, we write down the differential equations which govern the dynamics, right. So, for a simple mass spring damper, we have the second order dynamics. For the RLC circuit, we have a second order dynamics, so on and so forth, right, and these dynamics are basically differential equations, right. So, what we are going to actually do in state space modeling is to basically take the differential equation model of your physical system, okay, and then convert this nth order differential equation. N could be 2, n could be 10, so on and so forth, and we convert this nth order differential equation, which essentially determines the dynamics of your system, into n first order differential equations, alright. That is the basic approach to state space. And so, how many states we choose is basically one of the easiest ways to determine that is, it is basically the order of the differential equation which you use to model the system with, okay. So, if you have, for example, an RLC circuit, it turns out the number of states we need are only 2, because the differential equation which governs the dynamics is the second order differential equation, okay. There is of course a different way to also decide how many states we need, and the idea is essentially this. For an electrical system, we essentially say the number of states are basically equal to the number of energy storing elements. So, take a RLC circuit, you have the inductor and the capacitor, which are the energy storing elements, and so you essentially have 2 over here, right. If you have 10 inductors, 10 capacitors, you have a 20th order differential equation. That is basically the story, and then you have 20 states, alright. So, let us actually go to a simple example, and we will start off with the ubiquitous mass spring damper system. Okay, so we have as you can see here a mass m with the spring constant attached to this wall on the left, k, sorry, okay. So, you have a mass m, it is connected to this wall over here by the spring constant k, and then I have got a damper over here with the damping ratio of b, and I have applied an input force towards the mass in this direction, and so we are going to see what the dynamics are. Now, we know by the basic force balance equation, okay. So, the applied force, the total amount of applied force is distributed among each of these 3 components. So, by Newton's laws, we know the component of force along the mass is basically mass times acceleration, where x is the displacement or the position of the mass. Okay. So, we have the component of force acting on the mass, then we have a component of the force which is acting on the damping, or rather the damping resists this component of the force, and it is basically a function of the velocity, that is dx by dt, and of course, the damping ratio b. And then the final component is this is a spring constant over here. Okay. So, the component of force acting on the spring and the elastic force which it produces. So, these are 3 components. Now, we know from standard the transfer function approaches which Ramakrishna has already taught, the basic way to decide or to write down the transfer function of this one is to convert this into the Laplace domain, right. So, we apply the Laplace transform on either side. So, f goes to f of s, then you have m s square, s square comes because of the d square by dt square, then you get the x of s, the displacement in the Laplace domain. The damping ratio is a constant, so it stays as it is, and the velocity gets a s term, again x of s, finally plus you get a k x of s. Alright. Now, if you remember the basic definition of a Laplace of a transfer function, it was nothing but the ratio of the measured output to the applied input, in this case the applied force, alright, and that is nothing but 1 over ms square plus bs plus k. And then we know that when we correlate this with the standard expression for the characteristic equation, we know that we can derive properties of damping, the natural frequency, we can talk about stability, we can talk about performance, so on and so forth, all the standard things, alright. Now, let us see how we do this in the state space approach. Okay. So, I will actually be doing this derivation. So, the final state space model is actually going to look like this, and you can see that we actually have okay, and you can see that we actually have these 2 variables over here, x1 dot, x2 dot, these are actually the states of the system. And we will see what these other terms actually mean. Okay. So, let us see how we can actually say derive this. So, if we recall the basic second order differential equation. So, we had m d square x by dt square plus b dx by dt plus kx, right. Now, what I am going to do is to introduce a new set of variables. Okay. So, I will say a new choice of variables, and remember what I said, that because we have a second order differential equation, the number of states will actually be equal to 2. So, let us introduce 2 new variables. Okay. We will just call them x1, you can call them whichever you like, but x1 is a good choice, and x2. Alright, and specifically I am going to assign x1 is equal to x, which is the basic displacement, and x2 to be the derivative of the displacement, there is nothing but the velocity. Okay. Now, with these new choice of variables, let us see how I can actually write down the dynamics, and I can derive the what I am still calling as a state space model, which I have not formally defined, but we will come to that later. So, let us see the relationship between x1 and x2, and we will see from there. Okay. So, first we see that dx1 by dt is nothing but x2, right, because if I take the derivative of x1, I get dx by dt, which is nothing but x2 over here, right, and dx2 by dt, okay, is nothing but d square x by dt square, right. Now, this d square x by dt square, we can rewrite it by using our second order differential equation and by dividing with this factor m everywhere. Okay. So, this will simply become f divided by m, because I am taking m onto the left hand side, minus b by m dx by dt, okay, minus k by m x. Okay. So, I have just rewritten my d square x by dt square in this particular form, alright. Now what I am going to do, if you look at the first equation over here, you see that I have expressed x1 in terms of x2. Okay. What I would like to do now is to express x2 also in terms of x1 and x2 if possible. So let us see how to do that. So I will actually do this here. So we have this d square x by dt square, okay, and you can see that I have got this term f by m, that is obviously constants or the independent input, they do not depend on the states, right. So that stays as it is, and then I have got this b by m times dx by dt. Now if you look at what is this dx by dt, it is nothing but x2, right. So I will just write this as b by m times x2, x2 is nothing but dx by dt. Similarly, the last term I have over here is k divided by m, which is a constant, it does not depend on the state. So that will stay as it is, and then I have the term x of t, x is nothing but x1, okay. So this simply becomes x1. So this is my equation 2, this is my equation 1. If I combine equation 1 and 2, I get exactly this state space system, okay. And what you see is that dx by dt is related to the state x2, whereas dx2 by dt is related to both x1 and x2, but of course this is specific to this specific example we have considered, this need not be true in general. However, the first row in the 2 cross 2 states matrix will always be 0 and 1, and we will see the structure repeating even for a nth order state space system. And the inputs are always treated separately. So you can think these are the inputs, this is, if you look carefully, these are the actual dynamics of the system, okay. So here is where you have your accelerations, velocities and so on, and these are the states, okay. Now let us say for this particular system I also want to measure the output, because without measurement you actually can't do control, you can't do analysis, any such thing. So let us say I want to measure the system, the output. Now what are the two states which I have? As we have seen, the two states are x1 and x2. x1 is nothing but the position, x2 is the velocity. Now which you want to measure is entirely up to you depending on what problem you are looking at. Let us say I want to measure the position, okay. Maybe I have got say a position sensor in one case. In other case, if you want to measure the velocity, I may have a odometer or any or one of these things. So if you want to measure the position, I call my measurement as y, okay, and remember what is accessible to me is x1 and x2, okay. Assume I can measure only the position, or I want to measure only the position. So I write this in the form of this, all right. So this is my measurement equation, this is my measurement equation, okay, and this is my actual state space matrix as well as the inputs, all right. Now let us actually go ahead, we will come back to this in a slightly more complex example. We will also look at the basic theory of how to write a nth order differential equation in the form of state space systems. But the basic idea is always this: you start off with the basic differential equation, okay. You make a new choice of variables, and the number of such variables, okay, is basically equal to the number of is equal to the order of your differential equation, all right. So in this case I had a second order differential equation, so I am taking two variables. These variables are called the states. Once you make a choice of these two states, the idea is to relate the states with each other, all right, and then you essentially start to get these dynamics, all right. And finally, of course, for, as I said, for analysis, for control, all these things, we need to make specific measurements. So then you introduce a measurement matrix as well, okay, and you get this structure. Now we will actually see the more formal version of this soon. Okay, so this was a mass spring damper. Let us actually see a very simple simulation of this one. So let us say I take mass is equal to 1000 kilos, the spring constant equal to say 2000 Newton per meter, and the damping ratio to be 1000, okay. Now remember my A matrix remember this particular matrix over here 0 1 minus k by m minus b by m. So, it is actually called the A matrix, and we will see why it is called the A matrix a little bit later. So, when I substitute the parameters k, m and b in this matrix over here, okay, essentially what you are going to get is this one 0 1 minus 2 and minus 1. And then if you look at these inputs over here, I have a 1 divided by m. For the moment, let us assume f is equal to a unit step force. Okay. So, f is equal to 1 and 1 over m just becomes 0 and 0.001. Okay. So, this is the A, this is the B, and we will see what these things are later. And if I do a simulation of this, I will run through the code a little bit later. If we do a simulation of this, we see a step response of the following type. Okay. And you essentially see that this is a damped stable response and with a very small overshoot over here. And we have seen from the transfer function modeling of a mass spring damper that when you have this kind of a response, we can sort of guess what kind of poles that the corresponding transfer function would have. So, for this kind of response, it is very easy to see that the poles would be like this. So, you have a complex pair of poles and it is in the left half plane, right, which is why you have the stable and the damped response. Now, of course, we are in this so called state space version where the notion of poles do not really hold, but we of course want to relate how the system response comes with the notion of poles as well in the context of state space systems. Okay. So, one of the ways to do that is you have this matrix A over here. So, we see this is a square matrix. Okay. And one of the natural questions that come when we see a square matrix is what are the eigenvalues of A. So, let us compute the eigenvalues of A, and it just follows the standard procedure. You compute the determinant of S times I minus A, and when you do this, you see that the eigenvalues are essentially this. And for the same system, if you look at the transfer function, which is S square ms square plus bs plus k, and you compute the poles of this transfer function, you will get exactly the same values as the eigenvalue. Okay. So, you get minus 0.5 plus or minus j 1.3229, all right. So, in this particular case, we are seeing that the poles of the system are exactly equal to the eigenvalues of A. We will see this a little bit more formally why this is true, but this is very interesting because it shows that this new modeling approach of the state space system, at least with respect to say the dynamics of this kind, exactly corresponds to what we see from the transfer function modeling approach. Okay. So, once we are done with this, we have talked about states of a system, right. So, for the mass spring damper, we have said that the state, one of the states is the position, other state is the velocity, and we have done all these derivations over here. We have this model, we have a simulation as well, so on and so forth, but we have formally not actually defined what the state of a system is. Okay. So, the definition here is not a very polished definition, but this actually conveys a correct picture. A variable is called the state of a system, okay, because the future output of the system depends entirely on the current state value and whatever input we are going to give, all right. So, you have a system, I have modeled it by the so called states of the system, and the output of the system, the future output of the system depends entirely on the current state and whatever input I give in the future. Okay. So, I do not need to worry about what happened in the past, I will need to worry about the current state, and in other words it also means the future output, in other words it also means the future output depends on the past input only through the state and not through any other parameter. Of course, assuming you have done a good job at the modeling and you have not left out any variables or you do not have unmodeled dynamics. So, as long as you take care of that, the future output depends only on the past input through the state, all right. So, if I put these two things together, in effect this means that the state summarizes the effects of all the past inputs on your system on the future outputs. Okay. So, the state actually acts like a memory of the system. So, take for example, a simple circuit where I have a capacitor and I am applying a voltage across this capacitor, right. So, I look at the voltage drop across the capacitor and I am interested in the dynamics. So, we know that the current through the capacitor is basically modeled like this, right. Okay. Now, what I am saying is if this Vc, which is the voltage drop across the capacitor, if that is the so called state of the system, okay, this particular variable, I am saying that at time t equal to 0 or any specific time you fix, we can just say it to be equal to 0. At time t equal to 0, if you have a certain value of the state, okay, at any time in the future, okay, Vc of t will depend on whatever information you have in the past. So, the current value of the state, okay, and whatever input I am going to give afterwards. Okay. So, for example, at t equal to 1, okay, as long as I know what is the value of the state at time t equal to 0 and I know the kind of input I am going to give at time t equal to 1, I can always calculate Vc of t. I do not need to know what happened 1 hour before, I do not need to know what happened 1 day before, as long as I have the total information of the state as of now, all right. So, that is essentially it is loosely called as a memory of the system, all right. Now, we have talked about what is a state, we have done a little bit example with the mass spring damper. We have seen that we have the so called input structure over here, inputs over here, we have the measurements over here, and we have the so called state dynamics as I call them. Let us see this as a formal definition. So, we have seen an example with the mass spring damper where we have looked at all the inputs which are given to the system, we have looked at the measured outputs, we have seen how to write down the basic equation for that one. We have looked at what I have called as a dynamics of the system, though I have not really explained that, we will come to that, and of course, I have talked about the states. Okay. Now, what is the general form of a state space model, and specifically a linear state space model? Okay. So, specifically a linear time invariant state space model, and it is written in the following way. So, x dot equal to a x plus b u, y is equal to c x plus d u. Remember, all the variables are functions of time, x and u, and we are assuming that this is a time invariant system. So, the matrices a, b, c and d are actually constant for now. In general, this need not be true. So, let us look at this particular equation. The variable x is actually called as the state of the system, okay, and we had a definition of that. It is basically the memory, it captures what all has happened before. The variable y is the measured output, okay, and the measured output is really your decision, as well as it depends on the constraints of the system. There are some states which we can measure, some states which we cannot measure, and in general you may not even be able to measure states, all right, but for this particular lecture we will assume that y are the measured states, all right, and u over here is the input which we give to the system, and u need not be a single input, it can be multiple inputs, okay. We are looking at state space, so multiple inputs are permitted. Now, we have these parameters a, b, c and d. A is basically there are different words for this. I can call it as the dynamics matrix or the state matrix, or a much better word would be the interconnection matrix, okay. I will explain what this is. So, the interconnection matrix basically tells how different states of my system are actually connected with each other or related with each other, or I can say coupled with each other. So, if you looked at the previous example, the state x1, which was a position, is connected to the velocity through this parameter over here, right. So, x1 is connected to x2 through the parameter 1. Now, x2 dot is connected to the states of the system through these two parameters. These are the interconnection parameters as we call them, and they define the dynamics, they define how different states are connected to each other and so on. And interconnection structures are very important, although we will not be dealing with that over here. But for us, interconnection structures here are basically the elements or the values which come up when we connect states, alright. Then you have the matrix B. Now, okay, before I go ahead, please note the dimensions of the matrices are very important. So, let us say we are looking at a nth order state space system, nth order state space system, and remember that you get a nth order state space system typically from a nth order differential equation, alright. So, if you have a nth order state space system, the matrix A will be of dimension n cross n, it cannot be more, it is a square matrix of dimension n cross n. Okay. Now, let us look at the matrix B. So, B is a matrix, as you can see from here, B is a matrix which takes the inputs which I have applied to the system and relates them to the state. So, it basically tells how my inputs are actually connected to my states. In the case of the mass spring damper example which we took before, the input matrix over here essentially says that whatever force I have applied does not directly go to state number 1, because I have got a 0 in that entry over here, but this force directly goes to state number 2, which is the velocity by the way, through the factor 1 over m. Okay. So, what B captures basically is how the inputs actually affect the states. So, we actually call B as the input matrix. Next, we have this matrix C, and C can be called as the output matrix. We have already seen in the case of the mass spring damper, we had an example of when we wanted to measure only the position. Okay. So, we had an output matrix like this, where x1 and x2 is the state vector, and this particular row over here was actually the C. Okay. So, C is the output matrix. We are not going to be say dealing with the matrix D over here. D is actually called the feed through matrix, the feed forward matrix, and we will not consider that over here. Okay. So, let me just recall this slide. So, we have this the general form of the linear time invariant state space model. A, B, C, D are constant matrices, all the others are functions of time. The A is the interconnection matrix, it tells how different states are coupled to each other. B is the input matrix, it tells how my inputs affect states, which input affects which state and with what magnitude. C is the output matrix, it depends what I want to measure, and D is a feed forward matrix. Okay. So, A is a n cross n matrix, the interconnection structure, it is always equal to the number of states which we have. B is the input matrix. Let us assume we have m inputs, m could be less than n or even equal to n. So, B will be a m cross, B will actually be a n cross m matrix, and let us look at the output matrix C. Let us say we are measuring p states, okay, in which case C will be a p cross n matrix. Now, in general we could actually measure all the states if we have access to all the states, in that case p will be equal to n. So, we have a n cross n measurement, okay, output matrix. Finally, we have the matrix D, the feed forward matrix, which is basically p cross m. Okay. So, these are the 4 matrices which we are going to consider. We will be ignoring D for the rest of this lecture, we are going to look at basically A, B and C. Alright. So, this is the general form of the linear time invariant system. Okay. Now, we have always said that assuming we have a nth order say differential equation, how do we go from that to the nth order state space system, and let us look at the general derivation over here. So, consider an nth order differential equation which actually models a linear time invariant system. So, we have the differential equation over here. So, u is the input, y is the output in this particular case. Okay. So, we have these coefficients here which come about when you are modeling the system. Okay. Now, what we are going to do here is, as we have done in the mass spring damper case where we had the second order differential equation and we introduced two new variables x1 and x2, what we are going to do here is to introduce n new variables, because we have a nth order differential equation, we would expect to have n states. Okay. So, the way you would do that is fairly straightforward. So, let us say I have got I introduce a new variable called x1, x2 all the way to xn, alright, and again we have n because the order of the differential equation is n, alright. So, x1 I will relate it to the first variable over here y, alright. x2 I am actually going to call it as dy by dt, okay, and so on. Now, note that yeah, okay. Okay. So, I have x1 is equal to y, x2 is equal to dy by dt, and x3 okay. In a similar way, x3 is basically d square y by dt square. Okay. I can go on all the way to n, and basically what I would get is dn minus 1 y by dt n minus 1. So, this is exactly the same as the mass spring damper example where we had written x1 was equal to x and x2 was equal to dx by dt, exactly the same as that, except I have got n states over here. So, I have got the slightly longer looking expression, but it is exactly the same, right. Now, as we did in the case of the mass spring damper, we will now look at the derivatives of these states and we will see how these states are actually coupled with each other. So, if I take dx1 by dt, we see that it is nothing but dy by dt, and dy by dt as you can see is nothing but x2. So, I get x2 over here. Okay. Similarly, dx2 by dt is nothing but d square y by dt square, and d square y by dt square is nothing but x3. Okay, x3. I can go all the way here. Okay. So, I can go dx n by dt, okay, will be equal to, well, this would depend on all the states which we have over here, alright. So, let us see how to do that. So, dxn by dt is nothing but, if you look at this particular expression over here, is nothing but dny by dtn, alright. And how do we derive this particular thing? We take a look at our basic differential equation over here where I have dny by dtn, the nth order derivative of y, and we rewrite this expression, and the way you rewrite that, as we have done for the mass spring example before, would simply be u of t and take all these terms over here onto the right hand side. So, that becomes u of t minus a n minus 1. Then what do I do with this expression over here? I replace it with x n, alright. This particular term is nothing but x n. So, it becomes minus a n minus 1 x n, okay, minus in a similar way minus a n minus 2 x n minus 1, and you can go on like this, and then you have this expression over here a1 dy by dt, on I take it on the right hand side. So, I get minus a1 and dy by dt is nothing but x2 minus a1 x2, and then finally this expression a naught y. So, take it on the right hand side, I get a naught x1, alright. So, basically what I have done is exactly the same as a mass spring damper where I have written all the states in terms of the other states. So, we essentially have now the coupling between the states, the interconnection matrix, and when I put all of this in a matrix form, we want to know how that looks like. In the case of the mass spring damper, if you remember, we had x1 dot x2 dot was nothing but 0 1 what was that, k by m I think, yeah. minus k by m and minus b by m, alright, times x1 x2. Now we are doing exactly the same thing, except that we want to see how this looks on the nth order system, and it looks exactly like this. So you see that these first set of rows, okay, the n minus 1 rows which I am actually showing you over here, the n minus 1 rows are basically all the velocities which are related to the previous one. So x1 dot would be nothing but x2, x2 dot would be nothing but x3, so on and so forth, same as the mass spring damper case we have done. The final expression, the dxn by dt, it basically comes from this guy over here, okay. So this expression I have rewritten as the last row of this matrix, okay. And of course we have an independent variable here, the u of t, it is not a state variable, it is an independent one, so we take that outside. So this is basically my b u of t, this is my a x of t, and of course this is x dot of t. So x dot is equal to a x plus b u, this is a standard expression for a nth order differential equation, okay. So this is for a nth order system. And of course as before we want to measure the states. Now I can again decide which particular state I want. So I am just calling x bar as a state vector, which is nothing but x1 x2 all the way to xn, and in this particular case again I am measuring the first state, okay. I could also measure the third state, for example, in which case I would have a matrix like this. So if I measure the third state, I would just have a matrix like this, x bar, okay. Or I can even have a combination of measurements. So I can measure state 2 and maybe state 3 and 4, okay. So I would have something like this. That is really up to you. How you can measure depends on the sensors you have, the access to these states, so on and so forth. So this is the basic state space model of a nth order differential equation, and I have just shown you how we can derive this one, okay. And the logic for this basically follows the same process which we did for the simple 2 cross 2 mass spring damper, nothing more and nothing less, alright. Okay. Now let us work out a simple example. So we have this, so we have already done the second order state space model for a mass spring damper. We have seen the nth order derivation to derive a nth order state space system. Let us look at this simple third order differential equation and see how to derive the state space model, alright. So what we are going to do is to do what we have just done for the previous case. Since it is a third order differential equation, okay, we are going to define 3 new variables, x1, x2 and x3, alright. And as we have done before, we relate the first variable to y, the second variable to dy by dt, and the third one to d square y by dt square, okay, and the third one to d square y by dt square, alright. Let me write this here, okay. And the first thing which we always try to do is to find out the relationship between these states, essentially to compute the interconnection matrix. So for that we take the derivative of the first state and we find that it is nothing but dy by dt, and dy by dt is basically x2. So the derivative of the first state is x2. The derivative of the second state, so x2 dot, is nothing but d square y by dt square, and d square y by dt square is x3. Finally we have x3 dot, which is d cube y by dt cube, and d cube y by dt cube we can actually derive from this expression, alright. So what we do is to take all these terms onto the right hand side and then divide with the factor 2, that is going to give d cube y by dt cube. And so let us actually do that. So we get d cube y by dt cube is, remember I am dividing all the terms with the factor of 2, so it is 10 divided by 2, that is 5 u of t. This term is minus 4 divided by 2 d square y by dt square. So, minus 2 d square y by dt square, and then the 6 dy by dt becomes minus 6 dy by dt, and finally 8y becomes 4y. And what we do now is to replace each of these y's or the dy by dt with appropriate state. So, we know that y, as we have defined here, is x1, dy by dt is nothing but x2, and d square y by dt square is x3. Okay. So, this equation is nothing but 5 u of t minus 2 x3 minus 3 x2 minus 4. Okay, that is a final the last row of the state space model, and that is exactly what we get over here. And the first two rows in this case, as we have seen, will always be 0 1 0 0 0 1. And now we have the inputs in the final matrix over here in this form. And of course, again, for no particular reason I am considering that I am measuring the first state, that need not be true. I can measure the second state, or I can measure a combination of states, any such thing, that is really up to you. Okay. So, let us take another example. We will use a parallel RLC circuit, and we will try to derive the state space model. So, actually I have shown the final derivation over here. So, let us see what the actual circuit looks like. So, let us suppose we have a current source IS, okay, and we have connected this parallel with a resistor branch, an inductor branch, and a capacitor branch. Okay. And let us say we measure the voltage across the capacitor, you can call it Vc or V out as you like. So, this is C, this is L, and that is R. Okay. And I will further denote the current through the resistor being as IR, through the inductor being IL, and through the capacitor being IC. And now what we want to do is to write down the state space model for this one, and you can see that I have already considered the two states as being the current through the inductor and the voltage across the capacitor. And again, the reason for that is because this particular RLC circuit has two energy storing elements, one is the inductor, one is the capacitor, hence you will have two states and not more than that. Okay. So, how are we going to write the equations for this one? So, first what we are going to do is to focus on Vc and then on IL. Okay. So, the way that we would do it is, if you look at the current through the inductor, we know that the voltage drop across the inductor is given by the constitutive relationship, which is basically L dIL by dt is nothing but V, the voltage drop across that one, and specifically which V, I can write it as Vc itself, because the voltage drop across the capacitor over here is the same as the voltage drop across the inductor, which is in parallel with the capacitor. Okay. So, this is your equation number 1 when I take the term L onto the right hand side. Okay. So, that is 1 over L Vc. So, this is actually the first state equation. To write the second state equation, we will employ Kirchhoff's current law at this particular node by observing that the expression for the current through the capacitor is nothing but the total current which is coming in, okay, minus the current which is going through the resistance branch minus the current which is going through the inductance branch. Okay. Now, we see that this we have IL in this expression. So, I do not want to touch IL because we want the interconnection matrix between the voltage in across the capacitor and the current through the inductor to contain both terms. What I will do is to replace the other terms if possible. Is of course will stay as it is because it is an independent source. For IR, that is the current flowing through this resistance branch, we know that it is nothing but if you consider the voltage drop across this to again be Vc, because all these branches are in parallel. So, IR is nothing but Vc divided by R. Okay. IL of course stays as it is. What about IC? The current through the capacitor, as you know, is given by C dVc by dt. Okay. So, this is equation number 2, and if you plug these two equations into a matrix form, let me erase this one for 1 minute. Okay. So, if you plug these two equations in a matrix form, you are actually going to get this expression over here. Okay. So, let me show how we can do that. So, dIL by dt, that is the derivative of the first state, dVc by dt, derivative of the second state, and please see here this term C, the capacitance, I will remove it from here and divide it on the right hand side everywhere. So, that is 1 over C IS, 1 over C times R, and 1 over C times IL. Okay. And now we write down the A matrix and then the state vector. The state vector here is nothing but just IL and Vc, and I just have to fill in the elements of the matrix. So, dIL by dt is only a function of Vc with the 1 over L, and the other two, and for dVc by dt you simply just fill these two terms over here. So, this is your A matrix, it is the same as this expression over here. This is A, this is your B matrix, this is the input, alright. So, this is how the final state space model will look like. Let us say that you want to make a measurement of both the current flowing through the inductor as well as the voltage drop across the capacitor. In that case, your y equal to Cx will have the following form. It will be 1, 1, and you will have IL and Vc, assuming you want to make both the measurements, alright. So, let us look at the next example, which is again electric circuit. So, we have two sources, V input and Is, and we have got basically 2 resistors, 1 inductor and 2 capacitors, right. So, let us see what is the state equation of this one, and we are going to solve this again in the same way as the previous example. We see that we have 3 energy storing elements. There are 2 capacitors and 1 inductor, alright, and the voltage through capacitor 1 is written as Vc1, the voltage through the second capacitor is Vc2, those are the 2 states for the capacitors, and the current through the inductor is written as IL. Okay. So, the states for this, particular system will be Vc1, Vc2 and IL. Okay. And so, let us actually try to write down the dynamics of each of these variables, the time derivative of this one. Okay. So, let us start off and we can analyze this circuit in 2 ways, in 2 steps actually. So, the first step is to basically write down the nodal analysis at these 2 particular nodes. So, basically we are going to write the KCL at these 2, and in the second step we are going to apply KVL in this particular loop, alright. So, first let us look at node 1, okay, and we will write the Kirchhoff current law at node 1. And the way we can do this is we are going to assume all the currents coming in are positive, all the currents leaving that particular node are negative. Okay. So, they sum up to 0, that is a basic idea. So, at node 1 we have by Kirchhoff's current law, so Vc1 minus Vi divided by 4, okay, that is the current which is over here, and then we have the current which is leaving this particular branch here, okay, and that current is going to be given as Vc1, okay. Okay. So, this current through this I am going to write as by using this constitutive relationship I equal to C dV by dt. So, this is basically going to be C is 0.25, that is 1 over 4 dVc1 by dt, that is the current in this particular branch, right, and the current in this particular branch which is going out is just IL. Now, this is equal to 0. Okay. So, if I rewrite this expression, I will actually get dV C1 by dt is nothing but minus 4 IL, that is a term on the right hand side, minus Vc1 plus V input, alright. So, this is equation number 1. Now, this is the KCL applied at node 1. If I apply KCL at node 2, okay, I am actually so at this particular node I have the current IL which is coming in, okay, then I have this current which is going out, there is a current in this particular branch going out, and this IS is also coming in. So, I have IL plus IS, the two incoming currents. I need to now minus the two outgoing currents, okay. So, the first one will be again C dVc by dt, again I apply this constitutive relationship over here. So, I will basically get 0.5 which is 1 over 2, that is my C dVc2 by dt, okay, that is a current in this branch over here, and the current in this branch is nothing but the current in this branch is simply Vc2 divided by 1, alright. So, if I now rewrite this in terms of my dVc by dt, so I get dVc2 by dt is basically I multiply with 2 everywhere. If you take all the terms on the right hand side and then multiply with the negative sign, so you would actually get minus 2 Vc2 plus 2 IL plus 2 IS, right. So, this would be my equation number 2. Now, if I look at the loop equation, okay, that is this particular loop over here with the ground at the negative potential, these two as being positive defined over here. So, by applying KVL, I would actually get Vc1, it is minus Vc1 because of the polarity, plus the voltage drop across the inductor, which by the constitutive relation which I have written over here, V equal to L dI by dt. So, it becomes minus Vc1 plus 2 DIL by dt plus a voltage drop across this capacitor, right. So, plus Vc2 is equal to 0. So, if we rewrite this in terms of the derivative expressions, the states basically, so I get DIL by dt, remember I need to divide with 2 when I take it on the other side. So, it becomes 0.5 Vc1 minus 0.5 Vc2, okay. So, I had 3 states which I have defined. I now have the 3 first order differential equations for each of these states. So, I simply put them together. I have not yet talked about measurement, we will see the output, we will see that later. So, when I put all of this together, we get dVc1 by dt, dVc2 by dt and dIL by dt, okay. So, this is the state vector x dot, okay. This will be related by the A matrix times the states itself. So, Vc1, Vc2 and IL, and now this relationship is basically the ones which we have derived over here, okay. So, let us look at equation number 1 on the right hand side and we just plug in the terms which we have computed. So, it is minus 4 IL, so I get a minus 4 and a minus Vc1, so minus 1, Vc2 is not there, so it is 0. We will see what to do about the Vi a little bit later. Now, for dVc2 by dt, we see that we have a minus 2 Vc2 and we have a plus 2 IL, okay, and Vc1 does not come over there, it is a 0. Finally, for dIL by dt, it depends entirely on Vc1 and Vc2 and it is basically 0.5 and minus 0.5, this is 0, okay. Now, we still have to plug in the inputs because we have a Vi and a Is over here. So, what we are going to do with that is we have 2 inputs Vi and Is, okay, and what we would need is a 3 cross 2 matrix over here, because this is a 3 cross 3, it will be a 3 cross 2 matrix, alright. And we see that dVc by dt from equation 1, it depends on Vi, okay. So, I have a 1 over here, it does not depend on Is, so this is 0. dVc2 divided by dt, that is equation number 2, that depends on Is, and you have the constant being as 2. So, this is 2, this one 0. IL does not depend on ds, IL does not depend on is, as you can see over here. So, this is all zeros. So, this is the basic state space model for this electrical network. This is the A matrix, this is the B matrix, this is U of t, and this is x of t, right. And the measurements again are up to you. You may want to measure the current flowing through this inductor, in which case my measurement matrix will be 0 0 1, my C matrix will be 0 0 1, or you may want to measure the current across another 2 capacitors. So, the C matrix will change appropriately, all right. So, the entire derivation, the final state space matrices are actually given over here. Okay. Let us look at one more problem, which is on a couple mass spring damper. So, we have two masses and they are coupled by the spring with the spring constant K. Mass 2 is pulled in this direction by a force F, and mass 1 is connected to the wall with this damping, with a damper D, all right. And mass 1, it has a displacement x1, mass 2 has a displacement x2, and we are just going to assume that there is no friction between the mass and the ground over here, all right. So, there is no friction between these two, but you can easily incorporate that, that is not a problem. So, if you look at the basic way that we always write the differential equations or the dynamics for a mass spring damper is to always look at the force balance equations, all right. So, the applied force will have to be distributed across the individual components which are there. So, if you look at mass 2 first, okay. So, I am applying a force F, it resolves into two components. One is an acceleration component on mass 2, so that is mass times acceleration over here, and then the spring which is coupled between mass 2 and mass 1, and you have already seen in the previous lectures how to write these dynamics. So, it is basically K of x2 times x1, that is the displacement between the two things, between the two masses, okay. So, this is the second order differential equation for mass 2. In a similar way, we write the equation for mass 1. Note that the force F, it does not directly act on mass 1, it acts actually through mass 2. So, so term on the right hand side is 0, and because we have these internal forces, so mass 1 experiences an acceleration which is d square x1 by dt square, and then you have the damping which acts in terms of its velocity dx1 by dt, and K is again coupled between m1 and m2. So, we have K x1 minus x2, all right. So, as we did before, we are going to define the basic, we want to write down the state space model of the system. So, the first thing we need to do is to identify the states, right. So, the way that we are going to do, as we did for the original mass spring damper system, so we identify x1, okay, is equal to basically the position x1 itself. So, x1 of t is equal to x1 itself. Then we have a second state which I can call as x2, but I can also call it as v1, all right, it is the velocity. So, I call it as dx1 by dt, okay. These two states are for mass m1. Similarly, I have another state x2 which is the displacement of mass 2. So, I am calling it x2 itself, and sorry, this is x3 x2, and then I have a state x4, okay, which I am going to call as basically v2, the velocity of mass 2. So, this is nothing but dx2 by dt. Now, this notation is a little bit confusing. So, what we are going to do is to simplify this a little bit. We will remove this x2 over here. So, we have x1 and v1 as the states of the first mass, then we will call this as x as x2 and v2, right, otherwise everything else stays exactly the same. So, these are the states for mass m2. Now, all you need to do, since we know these already by the relation dx1 by dt is nothing but v1. So, one state is taken care of. The second state dx2 by dt is also taken care of by this expression, okay. And what we are left with is to actually to compute the time derivatives of these two states, and then you will get the interconnection matrix. So, If you go through the steps, you will actually see that dv1 by dt and dv2 by dt are essentially derived by using these expressions over here, right. So, we saw that v1 is if you take v1 equal to dx1 by dt, and now I am looking at dv1 by dt. So, it is nothing but d square over here, and I can rewrite this expression as we have done before and then derive these terms over here for dv1 by dt. In a similar way, you can derive the expressions for dv2, alright. So, we get these terms over here, put everything together in exactly the same way as we have done before. Remember that the states were x1 v1 x2 v2, and then you get this A matrix over here and the B matrix, alright, in exactly the same way as we have done before. So, this is the example for the couple mass spring damper. So, we have seen in a previous example for the simple mass spring damper that the eigenvalues of the A matrix are exactly the same as the poles of the corresponding transfer function, right. Now, let us see if this property holds in general, okay. But before we do that, we need to actually establish the relationship between the state space and the transfer function. So, given a transfer function model, how do you compute a state space model, or vice versa, given a state space model, how do you compute the transfer function model, right. So, this is a very simple derivation to show that. So, remember our basic equation was x dot equal to ax plus bu and y is equal to cx plus du, right. This is a general form of the basic state space system. Now, when I convert this into the Laplace domain, okay, so dx by dt, d by dt is basically the s term in the Laplace domain. So, you get s x of s, and then you get a x of s. Remember that A is a constant matrix, so it just stays as it is, as is for B, C and D. So, this is the first term of the Laplace expression, right. That is what I have written over here. Now, you take this term onto the left hand side and you subtract, and you are going to get these terms over here. So, Si minus A times x of s is equal to B times u of s, right. If this is confusing, I can just write this down. So, S x s minus A of x of s is equal to B u of s. Take the x of s term common out, and all you are going to get is Si minus A, okay, equals B times u of s. Now, so this is, we can call this as equation 1. Now, we have a second equation, y is equal to cx plus du, write this in the Laplace domain. So, this is the Laplace equivalent of y equal to cx plus du, that is this over here. Now, what we are going to do is to take this x of s, okay, which we have computed over here, okay, x of s is equal to Si minus A inverse B times u, right. So, I can write this 1 implies x of s is nothing but Si minus A inverse B u of s, right. So, I take this x of s and I substitute this. Okay, there is a small correction to be made in the slide. This is not u of x, this should be u of s, okay. All right, let us continue. Okay, so we have that x of s is equal to this expression. We substitute this back into this term over here, and then we derive this one, all right. So, y is equal to c, x of s is nothing but Si minus A inverse B times u, that is these terms over here, plus D times u, that stays as it is, okay. Now, we know that the transfer function is defined as g of s is equal to the output by the input. So, take the u terms common out of these two terms, all right, and then divide with u of s, and you are going to get this, okay. So, this is the basic relationship between the transfer function and the state space model. In this particular case, we are assuming A, B, C and D matrices are given to you, and the goal is to see how we can go and derive a transfer function, and this is the basic expression for that, okay. Okay, so let us actually solve a very simple problem. I will not go through the details, all the details are there in the slide. So, we have x dot equal to Ax plus Bu and then y equal to Cx. So, this is the A matrix, this is the B matrix, and this is the C matrix. And the objective here is to actually compute the transfer function given this state space model, and we know that it is given by this expression which we have just derived before, right. So, all we need to do is to plug in all these terms, and so for Si minus, so let me write down the expression again here, equal to C Si minus A inverse B plus D, all right. So, we need to first compute Si minus A and compute the inverse of that. So, Si minus A is basically this over here. So, that is basically Si is basically this S times I minus the A matrix was just this one, all right. So, when you actually subtract this, we actually get this Si minus A. Then you compute the inverse of that, okay. So, inverse of Si minus A is basically the adjoint of Si minus A divided by the determinant of Si minus A, okay. If you remember the basic expression of inverse, let us take a matrix, let me just give a different notation, I will call it as matrix M. So, the matrix M is actually computed by taking the adjoint of the matrix divided by the determinant of the matrix, all right. So, that is exactly what we have done here. Adjoint basically means these two terms are swapped and the sign of these two terms are reversed, that is exactly what has happened, and we compute the determinant here, all right. So, this is Si minus A inverse. Now, to Si minus A inverse, we need to multiply with we need to pre-multiply with C and post-multiply with B, all right. So, when you do that, so this is the expression over here. So, you pre-multiply with C and post-multiply with B, and when you do that, remember in our particular example, we had D over here is equal to 0, okay. So, the D term does not exist. So, this does not matter, the D term here really does not matter for us, we can ignore that, and what we get is C Si minus A inverse times B. You do all the multiplication and you are going to get this transfer function, right. So, this is a simple example to show, given a state space model, how to derive the transfer function. Now, it is important to remember that you may have made a mistake in the derivation. The simple way to double check is to compute the poles of this transfer function, right. So, there is a quadratic equation. So, you just use minus b plus or minus square root of b square minus 4ac by 2a, and you compute the poles. In this particular case, I think it will be minus 2 and minus 3, these are the poles, okay. And to double check that these poles are actually correct and that we have obtained these poles from the correct state space expression, what you can actually do is to compute the eigenvalues of the matrix A, and I will explain why that is true. We already saw a simple example of the mass spring damper that this was exactly the same. So, if you compute the eigenvalues of the matrix A, it turns out you will also get minus 2 and minus 3, all right. Now, let us see why this is actually true, okay. So, the eigenvalues of A are and the relationship to the poles of the transfer function, and it turns out as we can conclude in this last line, the roots of the characteristic equation of a transfer function, which are the poles, are exactly the same as the eigenvalues of the A matrix of the equivalent state space model, okay. So, the derivation is fairly simple. So, we have our expression which is over here. So, y equal to C Si minus A inverse Bu plus du of S, all right. Now, let me just rewrite this, remembering that the inverse of a matrix is the adjoint by the determinant, okay. So, that is what I have written over here. So, this becomes C adjoint of Si minus A divided by the determinant Si minus A, all right. You multiply with B, U and add the du over here. So, this entire thing is equal to y of s. Now, just do a simplification over here. So, this becomes C adjoint Si minus A Bu plus this term now goes onto the right hand side Si minus A determinant du whole divided by Si minus A. Alright. Now you see in the numerator you again have this u term as constant, it is of course a function of S. Okay. So take u constant, take u as a common factor, and then if you divide by u on the left hand side, you would actually get y of s by u of s on the left hand side, and that is equal to this expression over here. Alright. So this was basically y of s by u of s when I take u as a common factor in the numerator and then I bring it onto the left hand side. Now this transfer function you see is equal to this one with the denominator being Si minus A, the determinant of Si minus A. How do you compute the poles of a transfer function? We basically take a look at the denominator and we actually look at the roots of the denominator, right. We see the roots of the denominator are basically the determinant of Si minus A, it is exactly the same, alright. So computing the eigenvalues of Si minus A is exactly the same as computing the poles of your transfer function, okay. So that is why in the previous example we were actually able to prove I mean show numerically that the poles of this transfer function, okay, which are minus 2 and minus 3 are exactly equal to the eigenvalues which are also minus 2 and minus 3, and this is true in general, okay. Okay, so what we have learnt in this lecture was that we introduced the concept of a state and a state space system, and we saw why the state space systems are very important. They can actually model nonlinear systems, they can take care of multi input, multi output systems, so on and so forth, which the transfer function approach could not easily do or could not do in some cases. We essentially introduced the notion of the state. We saw the basic form of a linear time invariant state space system, which was the x dot equal to Ax plus Bu and y equal to Cx plus Du, right. And then we did a few examples for the state space modeling, and then we derived the relationship between the state space and the transfer function. Crucially, we proved that the poles of a transfer function are exactly the same as the eigenvalues of the A matrix of the state space system, okay. So this establishes that the dynamics we are looking at in the state space and the dynamics we are looking at the transfer function only for linear systems are exactly the same, okay. So what we are going to do in the next lecture is to look at since we are saying that state space can handle linear or even nonlinear systems, we will look at what are the basic differences between linear and nonlinear systems. We will look at why it is important to linearize a nonlinear system, and there is really good reasons for doing so, because handling nonlinear systems is extremely difficult, and we will actually look at the technique of the Taylor series to linearize a nonlinear system, and finally we will conclude with two really nice examples. One is the predator prey. We will write the nonlinear dynamics and show how we can linearize them, and finally we look at the van der Pol oscillator, okay. Thank you.